Alright, so in this problem, we have that the Earth's rotational period is once every 24 hours. If we have the flash running around the equator exerting 4.60 times 10 to the 7 newtons opposite to the direction that the Earth is rotating, after some time, the Earth's rotational period decreases to 39.5 hours. If we're given that the mass of the Earth is 5.98 times 10 to the 24th kilograms, and its radius is 6.38 times 10 to the 6th meters, how long was the flash running for this to happen? So, in solving this problem, the first thing that I'm going to do is write down everything I know, everything that's given to me in the problem. So I'll just read across and write down everything I see as it comes to me. So we have that the initial period, and when we talk about periods, we usually denote them with a T, is going to be 24 hours. So I'll write Ti for initial is equal to 24 hours. Alright, then we have that the force exerted is equal to negative 4.60 times 10 to the 7 newtons because it's opposite to the direction that the Earth is rotating. So this is a negative 4.60 times 10 to the 7th newtons. Alright, so after some time, the rotational period decreases to 39.5 hours. So we'll call that TF for the final period. It's equal to 39.5 hours. Okay, now we're also given that the mass of the Earth is equal to 5.98 times 10 to the 24th kilograms, and the radius is equal to 6.38 times 10 to the 6th meters. And what we want to find is the time for the periods to shift. So, the first thing I'll think about is, what do I know about periods, since this is a question involving a change in period? Well, I know that period is equal to 2 pi radians divided by angular velocity. So what we could really do is change these periods into their respective angular velocities. Then if we have that, this problem becomes a problem of a change in angular velocity and asking how long it took for that to happen. And that's something that we know how to do very easily. So I'm going to rewrite this as omega I for the velocity initial is going to be, and all I'm doing is rearranging here. I'm going to divide by t and multiply by omega. So this becomes 2 pi radians divided by t initial. Okay? And this is going to be equal to, if we plug in what we know for ti and we convert this to seconds, we get that it is 7.27 times 10 to the negative 5th radians per second, because we want our units of angular velocity to be in radians per second. Now let's do the same thing for omega f for the final angular velocity. And if we have 2 pi radians divided by tf, this, when you plug in your values and you convert to seconds, you're going to get that omega f is equal to 4.419 times 10 to the negative 5th radians per second. And this makes sense because the rotation is supposed to be slowing down and we're supposed to be having a longer period, so it makes sense that the angular velocity will be smaller here. So now that we know our two angular velocities, we need to figure out how to relate this to time. So I'm going to write down a kinematic equation. It's the first one that comes to mind when I think of a change in angular velocities and when I'm looking for time. This is just omega f is equal to omega I plus the angular acceleration times time. And this looks just like a normal kinematic equation that you would see, except this is for an angular case. So we know omega f, we know omega I. All we want to find now is the angular acceleration. So normally when you would go to find an acceleration, the thing you would want to do is use f equals ma. But since we're dealing with an angular case, we have to change that up a little bit. So the first thing that pops in my mind is I have the radius and I have the force, so that means I can find torque. So torque we will represent by tau, and I'm just going to write it right here below. So this is tau is equal to r times f. But I also know that torque is equal to the moment of inertia times the angular acceleration. So I'll set this equal to I, which is the moment of inertia, times the angular acceleration. So now I have three known quantities. I know r, I know f. All I need to know is the mass and the radius, which I know both. So I can solve for the angular acceleration here. So I'm just going to plug in some known values. we have RF, and we know that I, for a sphere, which we'll model the Earth as, is 2/5 mr squared times alpha. So now I can divide through and get a representation for alpha. I'll get alpha is equal to RF over 2/5 mr squared. Now these r's are the same because we're evaluating them at the equator. So this is the radius of the Earth, and r here is also the radius of the Earth. So what I can do is just go ahead and cancel one of those r's out because they're the same. So then this just becomes F over 2/5 m times r, which is the radius of the Earth. Now we know F, and we know we know mr. We know this whole quantity here. Something important to note is that we defined our force to be negative, so that means that our angular acceleration is going to be negative. So if we wanted to, we could rewrite this equation right away, just as omega f equals omega I minus at, and save ourselves the trouble of dealing with signs, because we know this is going to be a negative number. Alright, so the next thing I'll do is I will rearrange this equation for t. Now that we know omega f, we know omega I, and we know alpha. So I will subtract omega I, and then I will divide by alpha. So we have omega f is equal to, minus omega I, and then divided by the negative alpha, equal to t. Okay? So now I'm just going to plug in everything I know. Omega f, we have a quantity for, it's 4.419. Omega I, we have a quantity for, 7.27. You can see that when you subtract omega I from omega f, you'll get a negative quantity. That cancels with the negative here in order to give us a positive time, which we need. Now for alpha, we know f, it's a given. We know m, it's also a given. And we know r, which is also a given. So when you plug in your known values, you get a numerical answer that is 9.456 times 10 to the 8 seconds. So you can see this would actually take a very long time.